Bravo.
Shall we start?
Yes, sir.
May I know whom I am talking to?
Yes,
Yeah,
sir.
who is? Okay, okay. So let's
Yes,
start. Not waste
yes,
time.
sir.
Okay. Yeah. Okay. So before starting, a general question to all: do you have any doubts in mind about the things that I'm talking about for the last two classes? Any doubt in your mind? Yes. Anybody?
No, sir.
No, sir.
Okay. So is it that you are convinced with whatever I am saying or proving, or you are just taking it for granted that everything is okay? Are you questioning your own self whether things that I'm talking about, or rather, are you verifying everything from your book? Do you have access to books?
Yes, sir, we're doing that, sir.
So you have books,
Uh,
everybody?
Sir, a couple of us have physical hard copies, a couple of us have e-books, sir. That's what we're managing with the.
E-books.
Yes, sir.
Yeah, because the demand of the subject is that you should be going through books, because actually you are studying formalizations, you are studying grammars, you will be studying grammars, sorry. And as of now, you are studying languages, their properties, you are dealing with proofs, and all those things needs uh, that you patiently go through sentences, you patiently understand um, special terms like maybe, if and only, because those are constituent parts of the proof system, right? So each and every word counts. So if you don't have access to books, when you are attending classes, everything seems to be very simple because your teacher is guiding you through the process. But after some time, things will muggle up, right? So you need a book. first and foremost, you need a book. You need access to books, right? So next day, please confirm me. Anybody, please confirm that everybody has access to books. That is very important. Done?
Okay, sir. Okay, sir.
Sir,
Okay.
do you recommend
It's
any
a problem.
specific book?
Yeah, the Hoffman book, Ullman book is the book that I recommend, and that Professor Roy also talked about.
Okay, sir.
Introduction to Automata Theory, right, by Ullman Hofcroft, or Introduction to the Theory of Computing by Michael Sipser. So you can go for e copies of those books also, right? So if anybody of you have PDFs, you share among yourselves. Got my point?
Yes, sir.
Okay. Yeah. So without wasting any more time, let's start. So as usual, I'm going to the whiteboard mode. Let's check whether it works fine today. And as you requested, I tried to share my board, and I shared my board also, but I think you need to have the software called Miro that I'm using.
Sir,
Otherwise that board, yeah, I shared
sir,
the board also.
sir, but we were
Yeah.
not able to get
Sir,
sir.
we can use a browser. We don't need to install that.
Okay. So by
I've
getting through
checked.
the browser, can you access, yeah, can you access the
Yeah,
board?
sir.
Okay,
Yeah.
that's fine. So anybody who is able to access the board through a browser without having the software.
Actually,
So
sir,
please click.
I didn't get the link. So I didn't.
No,
I wasn't able to check.
no. I had posted the link to all the three sections, and that is how one of your friends has access to the board
Oh, maybe I didn't.
via the browser, right? So anybody who has successfully gone through the board through the browser, please guide your friends so that they can do the same thing, because it's a whole new platform. There is nothing wrong if you don't know. Got my
Sir,
point?
sir, we didn't get any link to like your particular board, like
Yes,
anything.
sir. We
But I
did
have
not get
shared.
any
Yes,
link.
sir.
Yes, sir. We
Yes,
didn't
sir. We
get
didn't
any
You
get.
did
link,
not.
sir.
Sure.
Okay, but I had shared my board from this Miro user interface, and it showed me that it was successfully shared. But I need to go through it again because I don't know
Sir,
the protocol of sharing board.
say you can do another thing. You can share. I mean, copy the share link and forward it to the. I mean, group email ID that
Will
we
it
have.
work? Will it work? Will it work?
Maybe. I mean, at least
Okay,
we will
okay,
get the link and then we can check
okay,
will it work or not.
okay. This is point number one, and point number two. Whatever board work I am doing is available in your book also. I am not writing or not talking about anything extra. The only extra part is my experience and my insight into the subject. And for that, you are spending time and listening to me. But whatever main things that are discussed are in the book. That is why I'm telling you that you should be going through books. But anyway, I can share PDFs also from Ullman's own PDFs. I can share, nothing, no issue. You can have a variety of documents from internet. Are you getting my point? So if I'm successful in sharing the board as you have suggested, I will try. If not, don't worry. You please be attentive. Please open up your minds and listen to me very carefully. Whenever required, you talk with me, get your concepts clear, and then when you are free, open up your books to verify that, okay, verify your learning system. That's the actual approach, right? Okay.
Okay,
Okay,
sir.
so as usual, yeah, let me start. So as usual, I will just recollect for the first 10 minutes what we had been talking about, and then slowly proceed. So we had been talking about designing, representing Actually, I'm also thinking of managing this lag between the whiteboard and my voice. So I'll be trying to speak a bit slower. Okay, representing um, representing languages accepted by. Please unmute. Please mute your microphones, everybody. So we are discussing on the topic called representing languages accepted by finite automata by uh, by 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 algebraic expressions, right? That is what we are doing. And what are these called? These are called regular expressions, or is named after the regularity of the languages that are accepted by finite automata, right? So it's a property. Regularity is a property. So languages accepted by finite automata are called regular languages, and the algebraic expressions that are used to represent regular languages are called regular expressions. So what we are talking about, we had a recursive construction of regular expressions in the last class, right? I also talked about some free algebra, free and complete algebra system called clean algebra, and told you that clean algebra totally conforms to the way regular expressions look, the way regular expressions are used to generate strings. All the axioms and all the postulates of clean algebra completely fits with the definition of regular languages. But before that, you need to construct regular expressions, right? And we had done a recursive construction of regular expressions. We also talked about that whatever we do in point number 1 and point number 2. So point number 2 was talking about some free algebra, and that free algebra, when applied to regular languages, it completely fits, right? So we can use the axioms with the concept that all the axioms of this algebra are fully satisfied by regular expressions, and we can use them to prove some certain properties of regular expressions and actually of regular languages. But before that, we need to construct regular expressions, and we had constructed regular expressions via a recursive construction. Why recursive? Because by now I have talked enough about the recursive properties of such languages that are accepted by finite automata. And I demonstrated that particular thing by the iterative and recursive definition of del hat that is central to the languages of finite automata. Agreed? So these are the two things that we discussed, and today I will talk about these two things, and today we'll also see that how this algebraic notation and construction of regular expressions actually help us to construct
So it's not appearing on
equivalent
the,
machines.
so
Yeah.
none of the writing is appearing on the screen, sir. After the second point, yeah, now it appeared just now.
Okay. That I cannot help because see, I am using a very high-speed fiber optic cable in my house. I have installed. So please bear with me. The whiteboard needs to update itself, right? So whenever it happens like this, you just keep on informing. Now, is it visible?
Yes, sir. Now it's visible, sir.
Yeah. So what I mean is, so in point number 1, we'll construct, and I had shown you how to construct recursively. And point number 2, I talked about an algebra, because from that algebra we'll find some certain axioms, and if we see that those that algebra conforms to the thus recursively constructed regular expressions, then we can derive many properties of such languages. That's the use of algebra. Okay, a general question to all: what is the purpose of defining algebra? Why we talk about algebra? Can you answer? I can give a very simple answer: because it generalizes the domain completely, and it helps us with unlimited substitutions, right? You can substitute anywhere. Any axiom can be substituted anywhere, right? Unlimited substitutions. So with substitutions, you can have a precise concept on how actually these strings look like and what are the properties of these strings. What are they going to do? So in point number 3, we are going to see that if regular expressions is a mode of expressing the language, so obviously recursive these regular expressions should be able to actually map to the machine that should accept the same language, right? Because by that picture that I had drawn, there is a correspondence like this. So every epsilon NFA, do you remember this picture? Every epsilon NFA has an equivalent NFA. Every NFA has the equivalent DFA. And all these three are essentially 3 modes of expressing finite automata. And regular expression is nothing but it gives an algebraic view to this system. So if we try to construct regular expressions, we need to define a purpose for doing that, right? So today I'm going to draw a correspondence between 1 and 2 and 3 if I name 3 as designing machine equivalence. So let me just quickly go through the construction. What did we tell? We told that if L is a language, by the way, what is a language? It's a short recollection. What is a language? Language is a collection of strings. Sometimes we call them as words. A language is a collection of strings from an alphabet that is used to generate strings by a closure operation called clean closure. So I can formally write a language something like this. So having defined this, if L1 and L2 are languages, and if we allow concatenation, we can say that L1 and L2 looks like this. X is a string from L1 and Y is a string from L2, where L1, L2 both belongs from sigma star, right? So how did we define sigma star? We defined sigma star as we defined the star operation, the clean closure operation as if we go on like this, concatenating every pairs and pairs and pairs, and having defined base cases with epsilons, no cases with phi's, we'll end up to some generalized definition, right? And it says that, okay, it is all LIs, sorry, it should be upper script, all LIs, all languages taken I number of times where I is infinity. So a language L may be thought of as realized 0 times, that gives you epsilon, realized once, that gives you L, realized twice, that gives you L square. Taking all these things, it's a notation that it is a clean closure operation. Done? So do you want examples? I can give you a short example. So let L1 be 0, 1, 0, and let L2 be 1, 1, 1, 0, 1, right? So what is L1, L2? L1, L2 is L1, L2 is all such strings, right? So 0 followed by 1, 1, then 1, 0 followed by 1, 1, then 0 followed by 1, 0, 1, then 1, 0 followed by 1, 0, 1, right? Did you get my point? So this is how you represent L1 dot L2. And how then I will ask you, so what is if I operate a string if I operate a clean closure operation on 0, 1, 1, what should be the strings of 0, 1, 1? It should be epsilon. That means this has not been realized once at all, right? So epsilon, because it includes no realization also. It is realized 0 times. So you have epsilon because of the star. Then in the minimal case, you have occurrence of 0. Then you have an occurrence of 1, 1. Then you can have an occurrence of 0, 1, 1. then you can have an occurrence of 110, then you can have an occurrence of 0110, infinite number of strings, right? So that is what is called clean closure. And apart from the star operator, which is of highest precedence, we have operators like the concatenation operation and the plus operators, and collectively they will use these three operations recursively to generate more and more strings of from some alphabet, right? So if we have sigma as an alphabet, remember sigma is always finite, right? So how did we construct? We made a recursive construction. What did we say? We take care of unreachability with phi. So what did we denote? Phi is a regular expression that denotes the empty set. Epsilon is a regular expression that denotes the set with epsilon. A single symbol A is a regular element of sigma is a regular expression that denotes a set A. And applying these three and making an induction on the number of operators, because these are all binary operators. So if you proceed with an induction on the binary operators, always you take care of at least two symbols on both sides of the operator. And if we say that if P and Q are regular expressions, then P plus Q, P dot Q, and P star are regular expressions also. Now I will draw a correspondence between all these constructive definitions of regular expressions, recursively constructed regular expressions, with how we can actually visualize machines. So what is phi? Remember, regular expressions are algebraic expressions capable of denoting regular sets. That means it should be capable of denoting machines that generate those languages, right? So in case of phi, if we are talking about an empty set, phi can be realized in the machine part as a very simple operation. You start at some initial state. There is some final state, but there is no reachability. This is phi. So initial state and final states are not connected. That is what I mean. So if they are not connected, we'll be talking about generating the empty set, right? So if you have some initial state and you never reach some final state, you say that the language is phi. Do you agree? How to visualize epsilon? So I am giving an intuitive view, right? And then I'll come to the formal view. How to visualize epsilon as a language? Very simple. You make the start state the accepting state. What does it mean? It means you actually accept epsilon. Do we agree? Yes or no? How to think that a single symbol is a representative of a language that contains a single string called A? Okay, so let us start at Q0. And on a single symbol, if we reach a final state, then we can say that the language of this machine is A. Now remember, let there are no other states than only these states. So I visualize intuitively a machine. I can visualize a machine intuitively like this. For phi, this is for epsilon, and this is for a single symbol called A. Yes, any question? Somebody unmuted? Do we agree? Yes or no? I want to hear a yes, and then I will proceed. Do you agree on the interpretation of, yeah?
Yes.
Hello? Yes or no? Yes?
Yes.
Yeah.
Yes,
So, yeah. So what if I consider these as some base cases and proceed with an induction on the operators star, plus, and sorry, let me write it in the proper precedence format. So these are the base cases where there are no operators, right? These are the base cases where there are no operators. I am just visualizing the base cases of the recursive construction of regular expressions. and I didn't take care of any operators, right? Now, what if I consider them as base cases of some inductively derived machines that justify these constructions? That if P and Q are regular expressions, so should be P plus Q, P dot Q, P star. And what if I take these as base cases and make an induction on the operators with the faith that all of these operators are actually binary operators, and at the least case for simulating or emulating each such operator, I need two symbols. And if we think of generating over them, then we can generate strings, right? So does it make sense? I can always take these as base cases with no operators, and then make an induction on the use of operators incrementally, and then try to justify that if P and Q are regular expressions, so should be P plus Q, P dot Q, P star should be regular expressions also. So I will intuitively ask you a question. Let P denotes a machine, let it be a black box that has some initial state and that has some final state, and the machine accepts strings that are represented by P, because P is a regular expression. This is machine 1, right? What is Q? Q is a regular expression. So Q should be denoting another machine that has some initial state and that has its own final state and accepts strings like this from some initial state to some final state, and those strings are represented by Q. Now these strings are represented by P. Let this be machine M2. Now, without any loss of generality, and remember, it's generalization that we are talking about by theorems. So we can always construct another, we can always add another common start state and join these two machines in parallel with epsilons. Can we do so? We can join these two machines over epsilon so this is a new start state Q0 that would connect with epsilon to the initial state of machine M1 like this. And as usual, machine M1 will perform its job as it was doing, unbiased of this construction, and it would reach its final state. So this is machine M1, this is machine M2 as usual. And there is another epsilon. So this is actually denoting OR, right? Because P plus Q is actually OR, right? I hope you understand. So another epsilon would be joining the initial state of machine M2, and let machine M2 function as usual, not concerned with such construction, and it reaches its own final state. And what if we make a construction from each of these two final states to a new final state over epsilons? Now my question is, if I have two machines P and Q like this, can I join them with epsilon to indicate an ORing like this? Do you object? Do you object to such construction? This is my question. Do you agree to such construction? Because I can argue that, okay, given two machines M1 and M2, that has some number of states called indicated by set Q1 and Q2. So in this construction, I will argue, if you argue with me, I will argue with you that, okay, I started with two set of states Q1 and Q2. Q1 is for M1 and Q2 is for M2. And in my new construction, I have a new Q that is mod of Q1 plus mod of Q2 plus 2. I have added only two states, Q0 and some final state F. And my Q is still finite. So I have not done anything that makes Q not finite, right? This is one justification of the construction. Justification 1. Another justification may be that I have not hampered how individual machines work. So individual machines work in the same way. It has its own initial state and it has its own functions that generate multiple strings and accepts, right? So I have not interfered. So I have done epsilon constructions only to the start states and only from their final states. So that is justification number 2. What is that? M1 and M2 function as usual. Do you agree? Yes or no? Yes or no? Yes. So with these two, justifications, I have made a very intuitive and very simple construction. And that construction is that if P was a regular expression representing all the strings of machine M1, and if Q was a regular expression that was indicative of all the strings of machine M2, then P plus Q is nothing but P union Q, and that is an OR. And that OR has been simulated or constructed like this with 2 epsilons in parallel. So if you start in Q0, you may take this path to accept a string S1, or you may take this path to accept another string S2. So that means you are actually accepting string S1 or string S2 written in regular expression format. So if P was actually denoting a set P and Q was actually denoting a set Q, set means a set of strings like S1, right? S1, S11 like this. And Q was a set of strings like this. S2, S21 like this. So actually I'm able to simulate the actions of both the machines and in parallel, and in that sense it's an OR. Now do we agree with this intuitive operation? Yes. So we need to check whether we actually can build machines like this. And I had given you 2 justifications that okay, I can always do something like this. So if I do something like this, nothing hampers my basic requirement of a finite automata machine, that it should have a finite number of states. Okay, I have added only 2 states, it's finite, and the machines M1 and M2 are actually behaving as they were behaving. There is no issue, there's no concern at all. So if I say that okay, machine M1 had the 5 tuple that looked something like Q1 sigma 1 del 1 Q1, let me indicate the start state of machine M1 as Q1 and start state of machine M2 as Q2, right? For simplicity, Q1 and the final state of machine M1 as F1 if this is the 5 tuple of M1, and if this is the 5 tuple of M2, if this is a 5 tuple of M2, for example Q2, it has a different alphabet, it has different transition, it starts with a different initial state, and it ends with a different final state. Now this construction that I had shown you with a very, very intuitive way, I can formalize. And as long as I can formalize, and if I'm successful in formalizing it, I can say that that particular intuition was right, was formal. So the construction that I made with justification 1 and 2, I will write that okay, the resultant machine M looks something like, has the tuple called Q1 union Q2 union Q0 F0, because Q0 F0 are my new start state and final state, Q0 and F0, right? So I add these 2 states to the set. So this is a set of states. And then I say that okay, I take the alphabet as sigma 1 union sigma 2, no problem, because in your new start state you may have a string. You don't know whether that string would be accepted via this machine or via that machine. Actually you have constructed an epsilon and fa, and you can go either by this way or by this way. So that is justifying the OR operation, right? So that is what I mean by taking union of the alphabet, and I define a new transition function del, right? So these were the del 1s and del 2s. I will define a new del. If I'm successful in defining the new del, then everything is fine, right? In the parlance of automata theory and machine construction, if I'm in agreement with that, with the rules of how to construct del, if I can formally approach and prove that okay, this way if I write del, it is okay. So this is the new set of states, this is the new alphabet of the newly constructed machine. This is the newly constructed machine, right? So This is how you construct, and you say that, okay, how to define del. Now you have the responsibility to define del. So del, see, let us define it intuitively. So del on q0, del on q0, if it gets an epsilon, it may go to q1 or it may go to q2, right? So I define del as very simple. Del q0 epsilon should take me to q1, q2. What is q1 and q2? The individual start states of the individual machines in 1 and 2. Not a big deal. Del of qa, a is the symbol of this union alphabet, right? So I'm defining del, the new del of the new machine. So del of qa, what should it be? If del of qa, if that symbol is an element of sigma 1, so it should follow the del 1, right, of qa. It should follow this path. It should follow this path, the machine M1 path. For q in q1 minus f1. Because now, why q1 minus f1? Because now I am not accepting by this final state. I should be rather going from this final state to a new final state. So what I do is, for some q in q1 minus f1, I'm just taking out f1 of the whole game, right? And a in sigma 1 union epsilon. So that way, when I'm doing an union epsilon, if you remember, when I defined epsilon and fa, I did some union with epsilon so that I can allow transitions on epsilon. Done. So what should be del of qa? Another way to define del of qa, if it goes through machine M2, it should be the transition function of machine M2, that was del 2 q comma a for q in q2 minus f2, because f2 is neither the final state of machine f2, because machine m2 also will accept via the common final state that we have designed, the common final state. So from this final state, it should follow with an epsilon to the new final state that we have defined. We have defined a new final state, remember? So here also we define so what are we doing? We are keeping, with these two del definitions, we are keeping the independence of machine M1. So del 1 was the characteristic function of how machine M1 behaves. So my new del will go through machine M1 as it was going, no problem. My new del will go through machine M2 as it was going, no problem. So I am keeping the independence of both machines. And that was my justification number 2. And my justification number 1 was that, okay, everything remains finite. This remains finite. This remains finite. And I'm successful in defining a del like this. No problem in that. So also del for final state of machine M1 should follow an epsilon and take me to a new final state. Also, the final state of machine F2 should take me, should be going to the new final state over an epsilon. Right. So essentially what I did is I took a union of the two machines. This was machine M1. This was machine M1. It has its own initial state, right? That was Q1. And it had its own final state F1. It was accepting strings like this. What I did was I took away the acceptance capability of F1 and rather let F1 slip to a new final state and accept. So the strings that was accepted from Q1 to F1 remains intact, because epsilon at the end doesn't add a new characteristic to the string that was getting accepted in M1, right? So it should slip to a new final state. And here what I do is I'm talking about machine M2, similarly like this, it had its own final state. And what I'm doing is I'm taking away the acceptance capability of F2 and saying that, okay, please accept via F2. So essentially I'm doing this, and I'm successful in defining a del, composite del for the whole new machine. This is a new machine. And I'm successful in defining the del of that machine via these definitions, right? Via these definitions. That preserves the independence of the two machines. And essentially, if P is a regular expression expressing the language of this machine, and Q is a regular expression expressing the language of this machine, this construction proves that sets P and this new machine is actually accepting sets P and Q. Okay, let me not use Q. Let me use okay. Let me indicate with the regular expression only, because it will interfere with the sets of with the states, right? So P plus Q is closed. That is what I mean. So regular expressions are closed with an union. Agreed or disagreed? Yes or no? So similarly,
Sir,
if our
could you also
induction
say that P
continue,
and
yeah,
Q are
yeah,
equivalent?
yeah.
So could
Please
you
slowly, please talk. Your
sir,
voice is breaking. Who is talking?
sir, me. Sir, raise my hand, sir.
Okay. What's your name? Yeah,
Sir,
what?
Projota, sir.
Okay, okay.
Sir,
Yes.
you also say that P and Q as languages are equivalent, sir, because both the machines go on to the same final state.
No, 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 no. You did not get what I was talking about. I didn't talk about equivalence of P and Q. I am talking about the closure operation of P and Q. What I'm
Okay.
talking about is if P and Q are regular expressions, they are expressing some languages, right? P is expressing some language, Q is expressing some language. Now, if P is expressing some language and Q is expressing some language, what are those languages? Those are regular languages.
Yes.
If those are regular languages, they should be having a machine counterpart. So let this be the machine counterpart for counterpart for regular expression P. That means all the strings that get accepted via this machine, that has the initial state and that has a final state and that has states in between. All the strings are represented by Q, because P is the regular expression for this machine. Q is the regular expression for this machine. I'm trying to find out the machine equivalence, right? And
Yes.
then what we did is, in order to get P plus Q, we made a construction by allowing these two machines to operate in parallel.
Okay.
And we joined the two machines. This is M1, this is M2. We joined the two machines over epsilon with a new start state.
Yes, sir.
And then we ended at a common final state with epsilons.
Yes, sir.
So epsilon, if your string is say 0, 1, 1, putting epsilon in front is not changing the string. Again, if your string is 0, 1, 1, putting an epsilon at the end is not changing your string also.
Yes, sir.
In fact, if your string is 0, 1, 1, you can place epsilon at all places. So you are taking the advantage of definition of epsilon, the characteristic property of epsilon, and joining the two machines in parallel. And you are claiming that, okay, I can always do such construction if I am within my limits and I am not disobeying the laws of machine construction or finite automata in general. And then we constructed something like this. And we saw that, okay, in such a way, we can always achieve this. And we deduce that, okay, in the regular expression definition, we say that if P and Q are regular expressions, so are P plus Q. P dot Q and P star, right? Now that particular claim of regular expression, I didn't establish that claim with machines. What I'm trying to do is, please try to get me. What I'm trying to say is, having said that if P and Q are individual regular expressions, Rajat, I am not talking about equivalence of P and Q.
Yes,
I'm
sir.
talking about individual P's and Q's, right? If P
Yes.
and Q's are regular expressions, P plus Q is a regular expression also. Now, to justify that claim, I took one approach to derive a machine. I
Okay.
can always have another approach via algebra. Got my point?
Yes, sir.
So I took this approach in this class of designing a machine, because designing a machine gives you a practical insight into the problem and you feel excited about that. Talking too much about algebra may be boring to somebody. I'm always ready to talk about algebra. I told you to go through clean algebra. And if you want me to do, I can do. But I took this approach of building a machine and proving this equivalence. Now I'm talking about equivalence. That what equivalence, Prajat? What equivalence? That P plus Q, if it is a regular expression, it should be equivalent to a machine that should be generating strings of both P and Q in a union fashion. Got it?
Okay, sir.
Is it
Yes, sir.
confident?
Yes, sir. Yes, sir.
Okay. Thank you. Thank you. Please concentrate. In my class, if you don't feel like if you feel like that today I'm feeling a bit sleepy, I cannot concentrate, please let me know, right? Because you need to concentrate. Now let us talk about P dot Q. So if P, I'm not talking about equivalence of P and Q, Prajat, right? I'm talking about two individual regular expressions,
Yes,
P
sir.
and
Yes, sir.
Q.
Got it.
We
Got
say
it.
that if P and Q are regular expressions, so should be P dot Q. Now the induction comes over the dot operation. So intuitively, if this is machine M1, what is P dot Q? P is a regular expression that generates all the strings of some machine M1. M1 has its own initial state Q1 and has its own final state F1. Got it? And it has many more intermediate states and accepts a set of strings. Those set of strings are indicated by P. Let Q be a regular expression that indicates the set of strings of another machine that has its own initial state, say Q2, and its own final state, say F2, and it accepts those strings, only those strings and only those strings that are reflected by Q or expressed by Q. So this is machine M2. So what is P dot Q? P dot Q means the strings X and Y. X is an element of the set represented by this regular expression P. See, I am writing it in capital, right? And Y are the strings represented by the set of strings represented by small q, because small q is a regular expression and capital Q is the set of strings represented by small q. So P dot Q is actually a representative of such strings as X dot Y. Do we agree? So what if I intuitively design the same thing? I make a common start state and push epsilon so that I can reach Q1, right? Or see, this can be done in a better way. Let us not put something here because we are doing a concatenation. It's more simple. So let us start at machine M1 only, because we start at strings with M1 only, right? So it starts with strings of M1 only. So let us have the start state of machine M1 as the start state of the composite machine that we are trying to design, and just connect the final state of machine M1 to the initial state of machine M2. And then what you do is you can either have an epsilon or accept by F2. You need not you need not do some epsilon like this. You just put a epsilon connector, right, with machine M1 and machine M2. That concatenates. So these are all strings that are represented by Q. I can say that are represented by Q with this notation. And these are sets of all strings that are represented by the regular expression Q. And this set of strings are realized by this machine M1 that has an initial state and a final state. This set of strings is realized by some machine M2 that has its own initial state and final state. And what I do is I just take away the final state capability of F1 of machine M1 because I have joined. So any string that was getting accepted with F1 will now follow epsilon and go to machine M2 to have strings of the form Y. So let X be a string of this machine. It was getting accepted by M1, and I am not accepting X alone now. So I have taken away the acceptance capability of F1, right? I have made this a non-accepting state. And then what I have done is I let this machine M1 to be connected to machine M2. So an epsilon from the final state of the then final state of machine M1 is going to some initial state of machine M2. I realize the dot operation and then accept strings called Y, such that X belongs to the set represented by capital P and Y belongs to the set represented by capital Q. And this is how I say that P dot Q is a representative of such set. Do you agree? Can I do this construction? Yes? Yes or no? So I repeat, I have a machine M1. Yeah, I have a machine M1. that is represented by the regular expression Q. It has its own initial state Q1 and it has its own final state F1, right? So it accepts strings represented by the regular expression Q like this, right? And this is machine M2 that accepts strings represented by, sorry, this is P. I'm sorry, this is P, and this is Q. The machine that accepts all strings represented by this regular expression, right? And then it has its own initial state Q2 and its own final state F2. Now what are we going to do? We are going to concatenate. We are going to concatenate P dot Q. We are going to do something like P dot Q so that we can have all strings of the form XY. X is from the representative set of Q and Y is from the representative set of Q. We want to have some strings like this. What is that we need to do? We need to just connect the final state of machine M1 with an epsilon to the initial state of machine F2, so that now machine M1 and M2 are thus connected with an epsilon, right? And we take away the final state capabilities of F1. So any string X that was getting accepted in machine M1 as a transition from its start state to some final state, the then final state F1 is not now accepted. I don't accept a single X right now. So I've taken away this final state capability. Rather, what I do, after having an X, with an epsilon, I go to this machine and I take Y also after me if I am X. So in a sense, joining these two machines means you are actually simulating a concatenation on P and Q, right? P dot Q. Agreed? Agreed? Okay. So
Yes,
please go through your book and go through the formal construction of what? Construction of del of the new machine. As I just constructed the del of for the union operation. Do you remember? I constructed del of this whole thing, right? Similarly, you need to construct a del of the new machine for the concatenation operation. I give you an assignment, right? Just to save time so that I can talk about the closure operation, the main closure operation of regular sets, the clean closure operation. So what is clean closure operation? You say that if P is a regular expression, so should be P star. That is what you say, right? Yes? From the recursive construction of regular expression, if P is a regular expression, P star should be a regular expression also. So what is P star? What is P star, by the way? If P is a regular expression expressing a set of strings, what is P star? P star is a realization of the set of strings, realized zero number of times, realized once, realized twice, realized thrice, any number of times, right? Right? Is it?
yes,
So
sir.
let P is a set of strings that are generated by some machine that as usual has an initial state and has a final state. And it accepts strings of the form X like this. Right? Done? Now if I say that, okay, I accept strings of the type X going from Q1 to F1, and I want to repeat this thing so that I can generate more and more strings of the type X. See, I am talking about type X, right? Why I'm talking about type X? Because if P is a regular expression denoting a set of strings, we say that X is a string with a certain property, right? That property I'm indicating with type. So if I want to recurse here, if I want to repeat the generation of strings, what I need to do? What I need to do? I need to take care of two things. One is that repetition may be zero number of times. That means this particular set of strings might not have an epsilon, but my new construction should be having an epsilon because P star always has an epsilon, right? Zero number of times. P realize zero number of times. That means epsilon. So whatever I do, I think of a initial state Q0 and a final state F0. And first of all, I should have a path from Q0 to F0 with epsilon because I'm going to develop P star. So first of all, I need to have an epsilon. Very simple. Then what I do is, okay, let this P representing the strings of type X. Okay, I keep it in red. Next, what I do is I join the newly constructed start state with the start state of the machine. This is machine M1, that is actually representing some set of strings that is as well represented by the regular expression P. Got it? So that from P I am going to generate P star. I first create a root on epsilon from my new Q0 to my new F0, and I take away, as usual, the accepting capabilities of F1, because I will repeat any number of times, right? What I do is I put an epsilon and come back to the initial state, and I put an epsilon and go to some final state. So if P was representative of the set of strings of type X that were supposed to be generated by some machine M1 also, I am repeating here like this, because the type of string X depends on the paths that take from some initial state to some final state, and I don't want to hamper that path. So this path I keep M as it was. I don't hamper with the working of M, right? So Q1 to F1, the routes that were followed, I follow and I repeat on epsilon. Again, I come back to Q1. Okay, I go to F1. I come back to Q1. I go to F1 like this. So P star, even if P doesn't have an epsilon, for example, these strings doesn't have an epsilon, right? P is a very finite sort of set of strings. It doesn't have an epsilon, and it is a finite shape also, right? It may be infinite shape also. What I mean is that this the property of strings X that are indicated by the regular expression P doesn't have an epsilon, but P star is repetition. If you remember, it's repetition of the set. Say this is a set P indicated by the regular expression small p. So it's a repetition of that set I number of times from I equal to 0 to infinity. That means I may bypass this machine, right? Not realized at least once means I am bypassing this machine, and I am bypassing with an epsilon. No problem. And if I have at all a string, so if P was, for example, P was indicating a set like 0, 1, 1, 1, 2, for example, right? For example, this was the language of this machine. Now what should be P star? P star should be, first of all, it should have an epsilon, then all the elements individually, then all the combinations of these elements, 0 followed by 1, 1, 0 followed by 1, 2, you can have 1, 1 followed by 0, again followed by 0, again followed by 0, again followed by 1, 2, any number of strings, right? Then P star. What are these? These are repetitions. So the language of the machine was, for example, 0, 11, and 12, 0, 1, 1, and 1, 2. So 0, 1, 1, and 1, 2 were accepted by some paths from Q1 to F1. So let there be 3 paths. One path takes on 0, one path takes on 1, 1, and one path takes on 1, 2, right? And that is how you accept these strings. And this becomes a language of this machine. So if at the instant you do a P star, a closure on star operation, you need to accept epsilon. Okay, I have a separate path, epsilon. And then I need to accept 0. Okay, I start from Q0, go this and take this path and accept. I accept 1, 1. Okay, I start here and I take this path. I start here, I take the path 1, 1 and accept. Okay, 1, 2, 1, 2. I start from Q0, take this path and accept. Now 0, 1, 1. Okay, I take this path on a 0 and then I come back and I take this path on a 1, 1. So I have 0 followed by 1, 1 and take an epsilon and accept. Is it? Everybody silent? Is it? Hello?
Yes,
Am I
sir.
audible?
Yes, sir.
Okay. So yeah. Okay. So let me end today's class with constructing the equivalent machine, and that is pretty interesting. So I left the concatenation of P and Q to you. Just go through and check. So how do I construct this? So we think of P star as a machine, a machine that accepts the language expressed by P, right? So this machine generates the language expressed by P. So in that case, P is equivalent to this machine, right? It's a representation of the language. So let it has Q, Q1, sigma 1, del 1, and then it starts at small q1 and it ends at f1. And in the final construction, I took away the acceptance capability of f1 so that I don't accept only strings like this, but I repeat any number of times and then I accept via epsilon, right? You remember? So this was the basic machine, and we want to construct this was being represented by P, and we now need to construct a machine that P star represents. So what we need to do? Okay, we need to define a new machine. Let this be the old machine M1. This be the new machine having the star operation, right? And let it be Q1 union my new start state Q0, right? And my new end state F0. So I will have Q1 union Q0 F0, very simple. And then I am not working with the alphabet remains same, right? Because I am working with the same P only, having a star on itself. I am not operating on a Q. So the alphabet remains same. So sigma 1 remains same. And let del be my new del. That is the point of interest. Del 1 was the del of this machine. So this del is the new del of the composite machine. Composite machine means having all of these. The basic machine, the two new states, and the epsilon connectivities, right? Epsilon connectives. So you define del as you start with new Q0, and you end at new F0. So this is the machine that we are going to construct. So the most important thing is how we formalize del. So what I can say is, if I'm in Q0, I can have an epsilon. And if I have an epsilon, I can directly go to, two places. I can go to the start state of the machine, or I can accept epsilon, right? Because I'm actually doing a star operation. So what I can do is, I can write it as set. I can go to Q1 because Q1 was the start state of the basic machine, or I can go to my newly constructed F0 and accept. Right? What is del of F1 epsilon? It goes to F0, right? So del of F1 epsilon, it takes me to F0. And also it takes me to Q1, right? So I'm in F1 with an epsilon. I can go back to my Q1 and generate more strings, or I can accept, right? So again, it's the same set. Q1. It's the same set Q1 F0. Done. And what is del of QA? Del is the transition function of my new machine. So I am in some state Q, and some I get some symbol. I want to make a transition. My transition will be exactly same as the machine, right? I am not defining these transitions. These transitions are, let it be a black box. This is a machine, right? The transitions of the machine that generate strings, I'm not touching there. So my del will be same as the del 1 of the old machine. So it would be del 1 of QA, same. So if the basic machine got a Q and a A, that pair was landing up in some state, my new machine would land up in that state only. But I have to define Q for Q in Q1 minus F1 and A in sigma 1 union epsilon, right? Because here you are defining epsilon transitions that take you back. For that, you need to include epsilon in your basic machine alphabet. And what you need to do is, you are talking about transitions of the basic machine. Okay, now Q1 minus F1, because now you are not accepting via F1. You have taken away the acceptance capabilities of this state F1, right? and now you are accepting with the new final state F0 going over an epsilon. So how does this look? This was my machine. I repeat once more so that it gets pinned in your brains. So this was a machine that has a start state Q1 and that accepts via some final state F1. Simple. It has some paths to accept strings of type X. Done. Now so this set of strings is generated by this machine M1 and is represented by some regular expression P. Now I want to simulate P star. That is what I want to do. So I want to simulate P star means I want to have an epsilon first, 0 times P, realizing P 0 number of times and realizing P any number of times. So the basic strings of type X and their repetition, right? That is what I'm going to simulate with the new machine construction. So what I do, I put an epsilon from a newly constructed start state Q0. I can always do that as long as the number of states are finite. I construct a newly construct a final state F0, and then I facilitate repetition over epsilon. Repetition means in this basic machine I can repeat myself, right, to generate strings of type X. So I need to go back from the final state to the initial state and again generate some X, right? So that's why I put a repetition on epsilon, and I don't accept, right? I only accept if I only accept by going to F0. I don't accept now with F1. So I take away the acceptance capability of F1 so that I can have any number of repetition. That any is very important. So that I have any number of repetition, including no repetitions, I join with epsilon also. Now I delete irrelevant things that I have scribbled. So I delete these things. So this is how your machine looks like. And you can also delete this to have a feel of the black box. So this is your black box, the machine. Right. So what is important is to have connectives from F1 back to Q1, to have connectives from Q0 to F0, and have from F1 to F0, and that is what I've done. So the newly constructed machine has its del Q0 epsilon. It goes to both Q1 and F0. Del of F1 epsilon, it takes back to Q1 and to F0. Del of F1 epsilon is F0. So that completes the part of. Let me tell it in a very comprehensive manner. So what I say is let's complete the recursive construction of regular expressions, and we have also seen the regular expression to machine equivalence. Right, and everything is based on the fact that I'm ending the class. Please give me 2 minutes. So everything is based on the fact that P is a regular expression expressing a set of strings with some property. That set of strings is called a language. What language? Regular language. And if at all it's a regular language, there should be a machine also generating the same language. If at all there is a machine generating the same language as is expressed by P, then we should have a path from P to conceptualize the machine. So next class, and what machine did we conceptualize? It's an epsilon NFA. Why didn't we conceptualize a DFA? So coming back to the old question that you had in your mind, what is the requirement of an epsilon NFA? I give you a more empirical viewpoint of that because we have done some experiments right now. We have visualized epsilon and we have conceptualized. Why epsilon NFA? Because epsilon NFA gives you the nearest perception of your human brain. Human brain has the capability of thinking in parallel, simulating things in parallel, right? And that you can do with epsilon NFA, the best. And given the theorems that say that, okay, epsilon NFAs can always be converted to NFAs, and the theorem that says that, okay, epsilon NFAs can be converted to DFAs, you don't worry actually, right? Because if you land up in an epsilon NFA, there is always a way to get a NFA and there is always a way to get a DFA. That would be actually helpful for computing, because computing requires deterministic steps, the steps that are defined in a very proper way, in a very proper format, no confusion, no ambiguity, and that is only given by DFA. So to conceptualize the purpose, what was the purpose? The purpose was to conceptualize that, okay, regular expression having been defined recursively like that is actually we are doing the right thing, because we are trying to visualize the machine equivalence. So we visualize the epsilon NFA machine equivalence, because that is the easiest way to conceptualize, because we are humans. We are conceptualizing machine right now, right? But when the question would be to run the machine for a purpose of acceptance, we need a DFA, because that would be a computer doing that, right? And for a computer, all the parallelism involved with non-determinism is bad. But for humans, that is good. That is a more natural way of perceiving. That is why for understanding regular expressions, we designed epsilon NFAs based on the fact that, okay, we have theorems and we can always convert back to NFAs and DFAs in turn. So that ends today's class. If you have questions, you can post in the group. And next class, I'll just do the opposite. From a DFA, I would be generating regular expressions, right? And that too, now from your intuition, you know that should be done recursively. No other way. So I will show you the other way around. And these two ways taken together, what does it prove? It proves a statement that P is a regular expression if and only if it denotes the language of a finite automata. That if and only if, the if part can be, you can think of the if part with this direction from a regular expression to a finite automata, and the only if part you can think of like this direction from a finite automata model to a regular expression, right? And that is why I go on telling you to read books, because if you don't read books, you will not be privileged to go through such sentences, and such sentences with such clause is the key to understanding this paper. Okay, thank you so much. Please jot down your questions. Keep your questions in mind so that we can have a discussion on Tuesday. Okay, thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah. Okay.
Thank you, sir.
Yeah. Yeah.
Thank you, sir.